All right, so last section we're going to take a look at today is 5.6. And 5.6 takes a look at vectors in three-dimensional space. Right? So everything that we've been doing so far has basically been on the xy plane. Right? So you can think of the xy plane if you were looking at, like, if this was a box, and you cut the front of it and the top of it and the side of it off, and you were looking at the back corner of the box, the xy plane is like the floor. The z-axis is coming up off, right? So if I had a table, the table would be the xy plane, and the z-axis would come right straight up from the table, okay, the 3D component. Because 3D is a little bit harder to visualize and to draw, we're not going to do what we did at the beginning of the week, all the sketching. It would work exactly the same. If you had two vectors in 3D, you can take this one, you can put this one on the end of it, and then you can connect the end of the black one to the red one. And then you'd have your 3D vector. But it's very hard to draw things when they're in 3D. Okay, so we're not really going to do any drawing. This coordinate system also follows what's called the right-hand rule. It's a right-handed coordinate system, which means if your index finger points in the direction of the positive x-axis, your middle finger points in the direction of the positive y-axis, then your thumb will point in the direction of the positive z-axis. So it tells you the directions of each axis. So like if the x-axis was pointing towards the back of the room, and the positive y-axis was pointing towards the door, then the z-axis would point straight up. If you do that with your left hand, it comes out backwards. Right? If you line up the x and the y-axis, your thumbs point in opposite directions. All right? So that's why it's called a right-handed coordinate system. If you're left-handed, I'm sorry. All right, so let's take a look first at how we would find the distance between 2 points in 3D. Okay, so this isn't even a vector problem. This is just finding the distance between 2 points in 3D. So for each formula, what we're going to do is we're going to recall how you do it in 2D, and then we're going to look at the pattern, and then see if we can extend the formula to 3D. So for 2D, this is one of the very first things we covered, very first day of class, how to find the distance between 2 points. It was the square root of the difference between the x values squared plus the difference between the y values squared. And we showed that that's really just the Pythagorean theorem. You got 2 points, and let's say this point is x1, y1. This point, x2, y2. And you want to find the distance between the 2 points. What you really end up doing is making a triangle out of it, like this. So there's my triangle. Connect the 2 points. And you're finding the length of the bottom side. And the length of the bottom side would be wherever you're at here, which is x2, minus wherever you're at here, which is x1. So if I put in marks, just as an example, this one's at 5, this one's at 1. 5 take away 1. Gives me 4, and that's the length of the bottom. Okay? Same thing with the height. You have to figure out how tall the triangle is. This is y2, this is y1. If you subtract those two numbers, it'll tell you how far apart they are, which tells you the height of the triangle. Once you know the base and you know the height, use Pythagorean theorem, and then you can find the hypotenuse. All right, so that's the distance formula in 2D. Now, in 3D, first of all, the coordinate would be a little bit different. It would have an x, a y, and a z part. And the formula to find the distance in 3D is very similar to the formula in 2D. We just have to add one more thing underneath the square root. Anybody have a thought about what we would add under the square root to extend the 2D formula to 3D? Jacob?
Divided by 2.
So we do have a formula where we divide by 2. We usually do that for the midpoint. When we're finding a midpoint, we add two things up and divide by 2. But in this case, it's going to look very similar to what's already there, but just extending it to 3D. So you're going to have everything you have now plus one more thing under the square root. Anyone think they see what you're going to have? Yep.
Is z2 minus z1
One more thing.
squared.
Squared. All right, so 2D, it's the difference in the x's squared plus the difference in the y's squared. And then in 3D, you add the difference of the z's squared. And that's pretty much how all the formulas that we're going to do today work. You just have to take the 2D version and make a small extension on the end of it, and then that makes it the 3D version. All right, so let's try an example. So I want to find the distance between these two coordinates. P1 is -1, 3, 2. And P2 is 4, -2, 5. Now, I called that a coordinate. It's still called, it's still called a coordinate. If you want to be more specific, you could call it an ordered triple. When we talk about 2D, you have an ordered pair. Well, in 3D, the coordinate is called an ordered triple. A coordinate is just kind of a general name. Describes location in any dimension. All right, so let's see if we can find the distance. Ben, if I want to find the distance between those 2 points, what's the first thing I should write down? We're going to have to leave a lot of room underneath it.
The formula?
Yeah, what's the first thing you would write down in that formula?
Oh, x2 minus x1.
Even before that, what else do you need?
The distance?
Okay, yep, so yeah, the distance equals. And what do we want to put on the right-hand side?
The square root.
Yep. So we want to put a nice big square root. And Jaden, can you tell me the first two things that I would subtract?
4 minus -1.
Yep, the x value from P2 minus the x value from P1. So 4 minus -1. And what am I going to do with that value?
You're going to square it.
Yep, we're going to square it. Plus. And Dominic, can you tell me the next two values I would subtract?
-2 minus 3.
-2, the y value from P2 minus the y value from P1. So -2 minus 3. And what do we do with that?
Squared.
We're going to square it. Plus. And Raymond, what am I going to put on the end here?
5 minus 2.
Z value from P2 minus the Z value from P1. Okay, let's just go through and see what we get. Colby, what's 4 minus -1?
5.
Squared?
25.
25. All right, Lacey, what's 2 minus 3? -2 minus 3.
-5.
And then when you square it,
25.
25 again. And Jacob, 5 minus 2?
3.
3 squared?
9.
9. So Autumn, the distance between these 2 points is how much?
Square root of 59.
Square root of 59. If they don't ask for a decimal, you can leave the answer just like that. If they want a decimal, just take your calculator, type in square root of 59, You get about 7.68. Okay, so any questions on finding the distance between 2 points in 3D? All right. So now let's take a look at vectors in 3D. So if you weren't here, this is going to review most of what we did all week, except doing everything that we did in 2D, now in 3D. So in 2D, this is how we write a vector. We have a horizontal component times I. Remember, we talked about I and J. Those are like Lego, right? Like building blocks. You can stack I's and J's together, and I moves you along the x-axis. J moves you along the y-axis. So by stacking together I's and J's, we can build any kind of vector we want. And if we want to go in different directions, we could use negative I's and negative J's. But in 3D, we're going to need one more unit vector. I will move you along the x-axis. J will move you along the y. And what do you think we're going to call the unit vector that will move you along the z-axis? Have a guess? Yeah?
Is it K?
Yeah, we're going to call it K. All right, so just going back to our picture, just kind of take a look at this. In 3D, this is I. Like that. It's 1 unit long, and it points in the direction of the x-axis. So the red one is I. K, let's do J next. So J is 1 unit long, and it points in the direction of the y-axis. We did these two before, I and J. The new one is K. So K is a unit vector, 1 unit long, and it points in the direction of the z-axis. So there's a picture of I, J, and K in 3D. Now we can stack I, J's, and K's together any way we want, and that allows us to move in 3D. If you make them negative, you could move in the opposite direction as well. So, any question on what I, J, and K look like? All 1 unit long, all pointing on a different axis. All right, so 3D. A would be your x-axis. I can't really say horizontal and vertical anymore because that applies more to 2D. So I'm going to switch to saying A is the x-axis component, B is the y-axis component, and C is the z-axis component. And this is how you write a 3D vector in unit vector notation. The A, the B, and the C would all be numbers. What's the other notation that we can use? Anybody remember what the symbols look like? It was the notation we used before we did the IJK.
Is that the position vector?
So yeah, it's when we talked about the position vector. And what did the symbol look like that we used? We use a symbol so we know it's not a coordinate, but it's all numbers. There's no letters, yep?
You kind of look like the greater than and less than sign.
Yeah, we kind of look like the greater than and less than. So if you don't want to write a vector with the I, the J, and the K, you can use just the numbers, the A, the B, and the C, but you'd have to write it like that. Right? You could use it's almost like the less than and the greater than. So you can write a 3D vector exactly the same way you write a 2D. Okay, 2 different ways. Again, notice we're not talking about sketching too much. Okay? That's not what we're going to focus on. Okay, so remember, the A, the B, and the C are the components of the vector. In 2D, I would say the horizontal and the vertical. In 3D, I can't really say that. It's the X, the Y, and the Z-axis components. All right, this is something we said on Monday. If you have a vector that has its initial point at the origin, anybody remember what the name of that is? A vector that starts at the origin. We said you can start anywhere you want, but the origin is the most common place. Dumb?
Position vector?
That's called a position vector. That definition isn't any different in 3D. A three-dimensional vector starts at the origin. That's called a position vector. All right, so 2D. If you wanted to find the position vector in 2D, you had to do the terminal point minus the initial point. So this is in 2D. Your terminal point has an x and a y value. Your initial point has an x and a y value. This is the exact same formula you have in your notes from Monday. So if you want to write down the recall, you can, but you already have that. Now, what we're going to do is extend the position vector formula to 3D. And we're going to do it just like we did the distance formula. We're just going to have to add a small thing onto the end, one more calculation. So anybody have a guess what we're going to have to add to the position vector formula for 2D to make it 3D? Yep. And
Z2 minus Z1.
comma, and then Z2 minus Z1. So you're still going to have to find the difference in the x's, comma, the difference in the y's, and if you were doing 2D, that's where you stop. But now in 3D, you're going to put a comma, Z2 minus Z1. So now the initial and the terminal point won't just be described with an x and a y value. It'll also have a z value. And formula, we're going to find the difference in the x's, difference in the y's, and then the difference in the z's. So if I was going to make a study guide for vectors, I would probably just write down the 3D formulas. I wouldn't write the 3D ones and the 2D ones, because 3D covers everything. Think about, if I gave you coordinates like this in 2D. And you said, well, wait a minute, you said not to write down the 2D ones. I don't know how to do that. I only know the 3D ones. Well, if those are the numbers I give you in 2D, what's the z part of each number? If those are two-dimensional coordinates.
Non-existent if it's
Right, it doesn't exist, so what would it be?
0.
0. So if you have a 2D coordinate and all you write down are the 3D formulas for the test, that's fine. A 2D coordinate just means that the z part is 0. So when you do 0 minus 0, you just don't even have to write that part. Right? So that's why with all the formulas we're doing today, I would just write the 3D version. And if you have to use it in 2D, just cross out the z part. You don't need it. All right, so let's try finding a position vector between these 2 points. So P1 is negative 1, 2, 3, and P2 is 4, 6, 2. Let's write the position vector using the angle brackets, and then if we want, we can write it with ijk after. Yep.
5, 4, -1.
Say it again.
5, 4, -1.
Yep. So subtract, and the order is important here. Do the P2 minus the P1. I'll write it all out just so you can see it. 4 minus -1. 6 minus 2, 2 minus 3. And then simplify. 5, 4, negative 1. Or, can somebody tell me if I wrote that with the ijk, how would that look? Jade?
5 plus 4j minus 1k.
Minus 1k. And again, if you just did minus k, that's fine. If you do minus 1k, that's also fine. So any questions on how to find a position vector in 3D? All right, so the next thing we looked at was adding, subtracting, and scaling. We did it visually in 2D, but then we also did it without sketching. That's how we're going to do it today. Okay, no sketching. So let's suppose that we have two vectors. Again, anytime you write a vector as a single letter, we talked about that, it should be bold. So if you weren't here, that's why I'm tracing over it, making it look bold. And if you want to add two vectors together in 2D, we learned, instead of drawing it, you can take the horizontal components, add them up, and take the vertical components and add those up. Well, in 3D, add up your x components, add up the y's, and then what else do you think I have to do to add two vectors in 3D? So, John?
What's the question?
What else, what do you think's under that box?
Z1 plus Z2.
Z1 plus Z2. Okay, so now we have to add the z-axis components. I also put subtraction in the same formula. If you want to subtract two vectors in 3D, the answer is going to be a new vector. And the horizontal component of the new vector would be x1 minus x2. The y-axis component would be y1 minus y2. And the z part of your new vector would be z1 minus z2. All right, let's look at this. Multiplying a vector times, or a number times a vector. Anybody remember what we called that? When you multiply a vector times a number, it begins with an S. Yep.
Scalar.
Scaling. Okay, scaling. This is called a scalar product. What are the three things that can happen when you scale a vector? The vector can get, yeah,
Too long.
yeah, it could get longer. What else could happen when you scale it? Yeah.
And change direction.
It could change direction if you multiply by a negative, so it gets longer, changes direction, or one more thing. Yep.
Get shorter.
It gets shorter. The way we scale a vector in 3D is exactly the same way you do it in 2D. You take each component and multiply it by what you're scaling, your scale factor. Take the x-axis component and multiply by the number you're going to scale by. Take the y-axis component, multiply by what you're scaling it by. And now take the z-axis component and multiply that by your scale factor. So it's just like a distributive property. We only had to do it to x and y in 2D. Now we have to do it to z in 3D. That's a scalar product. And this. That's a vector with double lines around it. Someone remind me, what does that symbol mean? Vector with two lines. That
Magnitude?
means magnitude. And we practiced magnitude last night in the homework, right? We do the angle between two vectors. You needed the dot product, but you also needed the magnitude. In 2D, that's how you do the magnitude. It's like Pythagorean theorem, the square root of the x value squared plus the y value squared. What do you think I'm going to add to this formula to turn it into the 3D version? Yep.
Plus z squared.
Which one, Z1 or Z2? Yeah, because we're talking specifically about vector V in this case. We're not even using W right now, and vector V is Z1. Okay. If we were doing W, we would have done Z2. All right, so finding the length of a vector in 3D, square the x component, square the y component, square the z component, add them all up, and then take the square root. Okay, so hopefully you're seeing that when you do it in 3D, it's really not, it's not really that much harder than 2D. And that's why I said most of today is going to feel like a review. So, all right, let's try a couple examples. So here are my two vectors. V is 2i plus 3j minus 2k. And W is 3i minus 4j plus 5k. Let's add those up. All right, so Jaden, when I add those up, what's going to be my new x-axis component?
You're adding them.
Yep, we're adding them.
You added 2 and 3. Do you add the words?
So to add them up, you want to do it just like that.
The 2 and the, no, the, yeah, the 2 and the 3.
The 2 and the 3. And that would give me how much?
5.
And what letter would be next to that?
Like after it?
Yeah. Because we still have to have all our letters that we had to start with when we write the final answer.
So do the eyes go in?
Yes. So the horizontal, the x-axis component would be
5i.
5i. All right. Dom, how about the y-axis component?
Negative 1j.
Negative 1j, or you could just put negative j, that's fine. And Raymond, the z-axis component?
3j.
Plus 3k. So that's the new vector that you would get when you add those two together. And Colby, if I wanted to write that in the other notation, how would I do that?
With angle brackets, it
Yeah.
would be 5, comma, negative 1, comma 3.
Yeah, that's it, 5, negative 1. On the test, you're not going to have to write it both ways, but I'll put in the directions which way I would like you to do it. All right, so that's adding them up. Let's do the magnitude of V. So Lacey, what's the first thing that, anytime we do magnitude, we always write down this symbol?
The square root.
Yep, I want to put down the square root of, and then we're going to have three numbers that we square. Normally it would be 2, but in 3D it's 3. Jacob, what's the first number I'm going to use?
5.
Where did you get the 5 from?
Combine V plus W.
Okay, so we're not finding the magnitude of V plus W. We're just finding the magnitude of V.
So 2.
Yep. So we don't need this last answer anymore. We can forget about that last answer. So the magnitude of V, we're going to have 2. And Autumn, the next number?
3.
3. And Ava, my last number?
-2.
-2. So let's do that out and see what we get. Vivian, 2 squared is how much? 4. Dominic, 3 squared?
9.
9. And Pete, -2 squared?
4.
4. And then when I add all those up, what's 4 plus 9 plus 4?
17.
17. Yeah. If the only thing they could ask you to do here is round that off to a decimal, is there any questions how you type that in on a calculator? All right. So that's how you find a 3-dimensional magnitude. And let's do a 3-dimensional scalar product. So now we're going to take W and we're going to triple it. So Jade, if I triple W, what would be my x-axis component?
9.
9.
9i.
Yep. So we're going to have a 9i. And Dom, my y-axis component?
-12.
What is it?
-12J.
Yep, -12j. And Raymond, what about my z-axis component if I triple W?
15K.
15k. So there is a scalar product in 3D. Any questions on that? Any questions how you would write it with the angle brackets? Okay, so there's adding, magnitude, and scaling. Dot product. So let's take a look at how to do a dot product in 3D. It's going to be exactly what you would think it would be. Okay, just extending the 2D version. So, since we just did this one yesterday, I'm not going to write the formula in 2D and put recall because we just did it. But anybody think they could tell me what are going to be the first 2 things that you see under that box? Yep. Huh?
X1 times X2.
X1 times X2. Good. What's going to be the next thing you see? Okay.
Y1 times y2.
Y1 times Y2. And if we were doing a 2-dimensional dot product, you're done. Multiply the X's together, multiply the Y's together, add them up. There's your answer. One more thing. What do you think is going to be the last thing you need to put to make this formula 3D?
Z1 times Z2.
And what's going to go right before it?
Right before it?
Yep, right here.
Oh, parentheses.
That's
Oh,
going to be
plus.
after it. Yes. Plus, then a parenthesis, Z1 times Z2. Right, so this is the extra part for 3D. So now you multiply the X's, multiply the Y's, and then multiply the Z's, and add them all up. All right, so let's take these 2 vectors and find the dot product. 2i minus 3j plus 6k, and 5i plus 3j minus k. All right, so using that formula, Lacey, can you give me the first step to finding the dot product?
You do 5 times 2.
So which one there is technically, well, I guess if you read it top to bottom, which one is the first x?
Oh, 2 times
2.
5.
Yeah, so let's just do it 2 times 5. We learned it doesn't make a difference, but just to follow the right order. So we have 2 times 5 plus, Jacob, what comes next?
Negative 3 times 3.
So negative 3 times 3. And Eva, what comes next?
6 minus 1.
Like this?
6 times negative 1.
Yep, 6 times negative 1. All right, and Autumn, if I do this out, 2 times 5 gives me
10.
and negative 3 times 3,
Negative 9.
and 6 times negative 1,
Negative 6.
negative 6. 10 minus 9 is 1. 1 minus 6 is negative 5. Okay, so that's how you find a dot product in 3D. What's the last thing that we did in 2D? And we had to use the dot product to do this. Yep.
Finding the angle.
Finding the angle. Okay, so that's going to be the last thing that we look at in 3D. That'll be a review. Okay, so this is the last thing that's review. The next thing I show you after the angle, that's going to be new, and that'll be the last thing for today. Okay, so angle between 2 vectors in 3D. All right, first of all, we're going to be doing an angle in 3D. We need vectors that are in 3D to do it. So here are 2 vectors in 3D. What trig function did we use when we were finding the angle between 2 vectors? It's the one that was on the left. Jacob?
Cosine.
Cosine. What was on the right-hand side in the numerator? Dominic?
Dot product.
The dot product. And what was on the right-hand side in the denominator? Yep.
The magnitudes added together.
The magnitudes on multiplied together. It's the exact same formula in 3D. And if you're like, well, wait, how can it be the same formula? It's because that's a 3D dot product, which we just talked about how to do, so that's a little bit different, over a 3D magnitude and another 3D magnitude. So these are all 3D things now. Well, I shouldn't say they're all 3D, but they're all calculated from 3D vectors.
That would be really cool if you could draw in 3D.
There are programs online, like if you just Google like sketch vector in 3D, and you can actually sketch it, and then the neat thing is you can rotate it. So you could sketch 2 vectors, and then you can spin it any way you want and look at it.
I mean, like if you're like, when you drew with your pen, it was like
Oh,
3D.
you mean just like holographic, like
Yeah.
in the air? Oh, okay. We're not quite there yet.
Okay.
Maybe someday. All right. So let's find the angle between 2 vectors. I'm going to use the same 2 vectors we just did in the last problem, because then we already have the dot product done. Let me just double check it. 2, negative 3, 6. Yep. And then 5, 3, negative 1. 5, 3, negative 1. Yep. So u dot v, we already did that. What was it? Negative 5. I think I gave the vectors different names, but I'm using the same numbers. So the dot product is negative 5. And the magnitude of u, how about Vivian, to find the magnitude of u, what's the first thing I would do?
2 squared
2 squared. Yeah, next thing.
plus negative 3 squared
Good. And last thing,
plus 6 squared.
6 squared. 4, 9, 36. 4 plus 9 is 13. And Dom, what's 13 plus 36?
49.
49. So P, what's the length of vector u?
7.
7. Usually that doesn't happen, we get a nice answer, but this time we did. Right, and Angie, could you set up my formula to find the length of V?
5 squared. 3 squared
Squared
plus negative 1 squared.
plus negative 1 squared. And that's going to give me, all right, so that's going to give me 25, 9, and 1. And Ben, if I add all those up, what does that give me?
35.
Let's see. Yeah, too bad it's not 36. That would have been a nice number we could have taken the square root of. But let's just go with that. So square root of 35. All right. Now, let's set up my formula to find the angle. So Dominic, using those 3 pieces of information, can you set up my equation to find my angle?
Cosine of theta equals negative 5 over square root of 35 times 7.
Yep. And Raymond, how am I going to get rid of cosine so I can get theta by itself?
Inverse cosine.
Good. So theta is the inverse cosine of negative 5 over 7 square roots of 35. All right, let's see what we get. Negative 5 divided by 7 square roots of 35. Close your parenthesis. Now this is another one that I'm wondering, do I need to fix my parentheses? I probably do. So just to be sure, I'm going to put the denominator in its own set of parentheses. Okay, just like that. If you can't see what I did, I'll put it over here. If you don't like those parentheses, I showed you guys a way around that. You could write it out as a decimal. Just use lots of decimals so we stay pretty accurate. And that gives me an angle of 96.93 degrees. Okay, so what we just did in the first, whatever that was, 40 minutes or so, we basically reviewed everything that we just did on Monday and Tuesday and Wednesday in 2D. Now, the last thing I'm going to show you is what's called a cross product. A cross product isn't something we've done yet. The reason? You can't do cross product in 2D. It only works in 3D. So that'll be the last thing. Any questions on that angle first? All right. So the first way we learned how to multiply 2 vectors uses this symbol, v dot w. And I specifically said to you, don't use the x. Because if you use the x, it means something different. It means cross product. And that's what we're going to look at today, cross product. So what is the cross product? It's a second way to multiply 2 vectors together. So that's why I said if somebody gave me a problem and said, here's 2 vectors, multiply them, I'd have to say, what do you mean? Which way? Do you want me to do it as a dot product or a cross product? If you gave me 2D vectors, there wouldn't be any question. I can only do dot product. But if you gave me 3D vectors, I have 2 ways I can do it. So again, cross product only applies to 3D. And the applications to cross product, there are some physics applications. We don't get into the application as much. If you take physics class, you might talk about cross products, depending on the level of physics you take. But again, not an application we're going to get into. If you take calculus at some point, you will get into the application as well. So engineering or anything like that. So, to do the cross product, unfortunately, you need to know, well, to do it the easiest way, you need to have more background information than you guys probably have right now. So, in order to do the cross product, we're going to do it a very special way that doesn't require you to have any more background information than you have right now. I'm not saying it's the fastest way to do it, but for where we're at, it's probably the simplest way, but not the fastest. So we're going to use a method called Sarris's rule to find the cross product. Let me show you how it works. When you have an actual problem, don't write this down yet because we're not ready. But this is what an actual problem will look like. It'll give you two vectors and it'll fill in numbers for the x, the y, and the z components. For now, I'm not filling in any numbers. I'm just using a1, b1, c1, a2, b2, and c2, but those will all be numbers. And the way Sarris's rule works is it's a very visual kind of thing. It's not really heavy, like calculations you have to do. The most complicated calculation in this whole process is going to be multiplying and adding. But what you multiply and what you add, we're going to figure out by making a kind of like a table. Or in our case, what we call a matrix. So remember, a matrix is just a series of rows and columns. It's like a spreadsheet. Okay, so we're going to make rows and columns. All right, and the way you want to set it up is like this. We're going to set up, because we're doing it in 3D, we're going to set up a matrix that's 3 columns by 3 rows. In row 1, I want you to just put the letters I, J, and K, and that's the same in every problem. In row 2, I want you to put these 3 numbers. They would be numbers in a real problem. A1, B1, C1. And then lastly, in row 3, I want you to write down these 3 numbers. A2, B2, C2. Okay, and that's the first step. Any questions on that? All right, so the next thing, I want you to take these 2 columns and make a copy of them. Don't move them. I want you to make a copy of them right next to it. So copy columns 1 and 2 to the right of column 3. So when you do that, you're going to take you're going to take column I, A1, A2, make a copy of it, and column J, B1, B2, copying it over. It's important you line these up, because if things are not lined up right, it's going to be hard for you to tell what you should do. So try to line everything up, the best you can. So once you copy columns 1 and 2 to the right, it should look just like that. Don't worry about the red and the blue yet. That's the last thing. So you have I, J, K, I, J, row 1, A1, B1, C1, A1, B1, row 2, A2, B2, C2, A2, B2. That's row 3. And once you do that, you create some diagonals. Okay, just to name, if you don't have different colors, I guess you could just name them diagonal 1, 2, 3, 4, 5, 6. I don't know why I use different colors. And the final answer to a cross product is to use this diagram and write something down from it. What we're going to write down are products. We're going to multiply some things together. What we're going to multiply together are the things on the diagonals. So the first thing we're going to do is find the product of everything on the red diagonal I called number 1. So you're going to multiply I, B1, and C2 together. And remember, the B1 and the C2 are going to be numbers. So it could be like I times 2 times 3. So that would be 6I. Right? But those are going to be numbers. Next, you're going to multiply together everything that's on red diagonal number 2. J, C1, and A2. And it's hard to remember that it's J, C1, and A2. That's always what it is. But if you make this diagram, you don't have to memorize J, C1, A2. All you have to do is look at your diagram and look at the diagonal. Okay, it's too much to memorize. And then you're going to do it again. You're going to find the product of what's on red diagonal number 3. K, A1, B2. And notice what you did with the first 3 in red. Add, add. With the ones in blue, you're going to multiply them together, just like the ones in red, but you subtract them. So multiply everything on blue diagonal number 1 and subtract it. Multiply everything on blue diagonal number 2 and subtract it. Multiply everything on blue diagonal number 3 and subtract it. And once we fill numbers in for all 10 of these letters, then it looks a lot simpler. When we did a dot product, the answer was always what kind of thing? Yep,
A number.
it was always a number. When you do a cross product, the answer is another vector. So it's totally different. The result of a cross product is a new vector. The result of a dot product is a number. All right, so let's try an example with numbers. We can come back to that diagram if we need it. Okay, so here's our 2 vectors. Find the cross product. So V is 2i, 3j, 5k. And w is I plus 2j plus 3k. All right, let's start with row 1. In the first step, what did I say to put in row 1? Yep.
I, J, and K.
I, j, and k. What did I say to put in row 2? Vivian?
A1, B1, C1.
And in this case, those are
2, 3, and 5.
2, 3, and 5. Yep. And what's going to go in the last row? Yep.
1, 2, 3.
1, 2, 3. Okay, there's your first step. Now, what do I do with that? My matrix isn't quite done yet. I need to do one more thing, and then I can start using the matrix to do stuff. Tom?
Copy the first 2 columns on the right of the third column.
Yep. So let's put down IJ, 2, 3, 1, 2. Now we're ready to write the final answer. This is purely to help us to remember what gets multiplied together. And it's easier to see it than to memorize all 6 of these products. Okay? So the red diagonals go down into the right. The ones that you add go down into the right. So let's circle them. Down into the right. Down into the right. Down into the right. When you circle a diagonal, it has to have 3 things in it. This is not a diagonal. That's a partial diagonal. Doesn't count. Diagonal has to go through all 3 rows. And that's all of them that go down and to the right. So multiply the ones that go down and to the right and add. What's I times 3 times 3? Yeah,
9,
9. Then what's j times 5 times 1?
5J.
5j. And j, what's k times 2 times 2?
4.
4k.
K.
Yep. All right. So that's the first part. Those are the ones that go down and to the right. Now, subtract the ones that go down and to the left. All right. So let's do those in a different color. Down and to the left. Down and to the left. That's everything that goes down and to the left. So minus them. That's the part people forget. They forget the minus. Raymond, what's k times 3 times 1?
3K.
3k, and remember to subtract it. If you subtracted something that had a negative in it, then it would turn into a positive. Okay, so follow your same rules for arithmetic you always would. Now subtract. What's I 5 2? What's that come up to? Yep.
10I.
10i. And what about j 2 3? Oh, Lacey?
6J.
6j. Remember, subtract it. Now, just combine your like terms, and that's your final answer. 9i minus 10i is how much?
Negative I.
Negative I. 5j minus 6j. Oh, Ava?
Sorry, what was the question?
5j minus 6j.
Negative 1.
Yep, negative j.
Oh, negative J, yeah.
And what's 4k minus 3k? Autumn?
K.
K. That's the answer. So when we do a cross product in 3D, that's what you get. So the last thing I want to finish up with is I want to multiply them, again, same two vectors, but let's switch the order. What happens when you switch the order normally when you multiply? Say two numbers. If you switch the order, what happens? Yep.
Still the same.
Stays the same. Nothing happens. Well, let's try it here. So what's going to happen when we switch the order is the two rows with numbers are going to switch places. The ij, k, ij stays the same. And if I was doing this problem from scratch, I would write the 3 and then make a copy. But we already have the problem right here, basically. Just swap these two rows. That's going to switch the order. 1, 2, 3, 1, 2. And then 2, 3, 5, 2, 3. Okay. Let's multiply the down and to the right. 1, 2, 3. Okay. Colby, I25 gives me how much?
10i.
10i. Lacey, J32.
6J.
6j. Jacob, K13.
K3. 3K.
3k. So those are the down and to the right. Now let's do the down and to the left. I circle them because I find it easier so I don't get messed up. So minus, Autumn, what's K22?
4K.
4k. Ava, I33.
Negative 9I.
Good, you have to remember we are subtracting it. And J15. Pete?
5J.
Yeah, and remember, you are subtracting it. You got to remember the subtraction, okay? 5j. Let's combine like terms and see what we get. What's 10i minus 9i? Dom?
10i minus 9i. 1i.
So 1i. 6j minus 5j. Vivian? just J. And Angie, 3K minus 4K.
Negative K.
Negative K. That's the answer we got when we did W cross V. There's the answer we got when we did V cross W. What's the difference between these two answers? They're not the same. But if you know one, you automatically should be able to know the other one at this point without doing this ever again. Yep?
Well, first, shouldn't that be a plus J?
Yes, thank you. That is a plus J because it's 6 take away 5, which is a plus J. Yes.
Isn't it the inverse?
Yes, it's the opposite. This was a negative I, this is a positive I. This was a negative J, this was a positive J. That was a positive K, that was a negative K. If you switch the sign of every number, that gives you the other one. So now when you have to find W cross V and V cross W, you don't have to do it twice. Just do it once and then take and switch all these the signs, and there's your second answer. Okay. So that's how you do a cross product. All right, so let me put up the homework. So the homework is on page 363, and then there are 2 problems I want you to do that are not in the book. So 15, 17, 29 to 35, 41, 43, 51. And then take these 2 vectors and find the cross product. V cross W and W cross V, but that's not really 2 different problems based on what I just told you. What I'm going to do, I'm going to pause the video so that way I can put a list of topics from the test in it. I'm not going to have time to do that while you guys are here. So I'll put the list of topics in the video. And then if you have any questions, you can send me an email or I'll be here after school today.